Hello and welcome back to Calculus 2, section 8.3 on trigonometric integrals. Take two, yes. So that's why we're so official. In tonight's lecture, we are going to reflect upon. All right, guys. So we need trigonometric identities. The most important trig identities to survive this section are the following five that you must know, even if someone shakes you out of bed at 4:30 a.m. and asks you. Sine squared x plus cosine squared x is equal to? 1. Jean, good. So this is the main equation, and you can divide everywhere by cosine squared to get tangent squared x plus 1 is equal to secant squared x. Or you can go back to the main equation, divide everywhere by sine, and get 1 plus cotangent squared x is equal to cosecant squared x. These are called Pythagorean identities. And each one of these you can solve for either sine squared or cosine squared or tangent squared or 1 or so on. So technically there are 9 equations here, right? Because you can flip them in any other way. So that's one set. We're going to put that in the blue box. And the other two equations that you must know is that sine squared x is equal to power reducing. Let's go.
It's like cosine 2x.
Yes, 1 minus cosine 2. This is why you need to work in groups now. All right, and for the exam, you can work in groups, and I'll split the grade evenly between all participants per exam. So, yeah.
I don't think you want to do that. I think splitting it by points or by percentage.
By same, whatever you want. 100% is 100 points, so it's good.
And what if the group takes multiple exams, and then you just grade them individually?
No, one exam per group. So you guys can do that in groups. It's okay. In one of the classes, I had the group of 8 for the lab. It's awesome. They definitely scored 100 on the test. Divided by 8 per student. All right. So welcome to the trigonometric integrals, where if you don't know these formulas, you just skip this in the next section. So we have now basic integrals, which you guys already know from Calc 1. Stuff like this: integral of cosine to the 9x sine x dx. So this is still the part of this section, even though you learned this all the way back in a u sub 5.5. So for this one, you know that u is equal to cosine x, du is equal to negative sine x dx. You put these negatives in, and then you have negative integral u to the 9 du, which is negative u to the 10 over 10 plus c. And then we go, I don't care about u, I care about the x, which is negative 1 over 10 cosine to the 10x plus c. So this is a standard Calculus 1 u substitution problem, which is still going to be relevant in this section, and you can get it on exam 2, final exam, later on Calc 3, and so on. Now, what is Calc 2 type of fun what is the upgrade that we are looking for? Where now we are going to take a look at the problem, the same problem as before, cosine to the 9. Okay, so cosine to the 9 x, and now we're going to have sine cubed x dx. So clearly this problem is spicier, right? Because we have sine cubed now. And this is where the calculus 2 begins in terms of the trig functions. So you look at this and you say, well, if I want to do u sub and use cosine for u, as we did in a previous problem, then I need only one sine for the du part, which leaves you with a sine squared extra, and you need to get rid of it. So that's the type of thinking that you need to adopt to survive the entire section and the next section, which is trig substitution. So you're looking at this and you say, I can deal with the cosine to the 9 with a single sine. So you are going to peel off, so you still have cosine to the 9x. You are going to peel off single sine, and you are going to keep that in a bank for du later on. So now you see that you have this extra sine squared that you need to get rid of. So how do we get rid of that sine? Well, you transform those into cosines, because the sine squared is 1 minus cosine squared, so that will get rid of this sign here. So you are now using Pythagorean identity that says 1 minus cosine squared x, and then you do the arithmetic to deal with this problem. So now we have integral of cosine to the 9x minus cosine to the 11x times sine x dx. And you can distribute sine and create two integrals now, because you have a subtraction, right? So now you have the integral of cosine to the 9x sine x dx minus another integral of cosine to the 11x sine x dx. You do not have to split. You can go with the u sub immediately, or you can split. It doesn't matter, because either case you have u equal cosine x du equals negative sine x dx. So we have to put in these minus signs everywhere, and that will give us negative integral u to the 9 du plus the integral of u to the 11 du, and then you integrate negative u to the 10 over 10 plus u to the 12 over 12 plus c, and then we have negative 1 over 10 cosine to the 10x plus 1 over 12 cosine to the 12x plus c. So this is what the Calc2 version would look like, where you have to use those identities to get rid of the extra sine squared that was introduced because we had sine cubed to begin in this problem. Now this problem can work backwards. Obviously you can have your cosine to be with a smaller power, and then you can leave a cosine in a bank for du and have u equal sine, right, and go through the same calculation just the other way around, which is okay. So that is what we would call vanilla problem, because the hard ones are actually the ones that have all even powers where this is not possible. So if I have integral of cosine squared x sine squared x dx, what we did before cannot be done now. Because if you peel off one sine or one cosine, you cannot transfer the rest, right, to the other trig function. If you are to try, I'm going to erase this because it's wrong. if you try to peel off 1 sine x to leave it in a bank for du and use u equals cosine just like before, you have issue that this sign cannot be transferred into cosines because the transfer formulas are all squared. This one is not squared. So there is nothing you can do about this, which means that the problem cannot be solved using the previous method. Well, that's okay. We're not gonna panic, not gonna cry, because we can use something else, right? So what you have here are two functions, sine and cosine, both of them squared, right? And if both of them are squared, you can use those power reducing formulas to convert these formulas, to convert both of these into single cosines. So 1 plus cosine 2x over 2 times 1 minus cosine 2x over 2 dx. So now you work this out. When you multiply these, well, first you kick 1/4 outside because half times half is a quarter, so kick that out. And you have now difference of squares, right? So you will have 1 minus cosine squared 2x dx, which is where you realize that you have to use the formula again, which is not a big deal. So 1/4 integral of 1 plus, sorry, we first have the 1 minus, and now we have, for cosine squared, we have 1 plus cosine 4x this time, because we are starting with 2x. Every time you use the formula, it doubles the original angle argument. So we started with x, used the formula, became 2x. Now we are using the power reducing formula on 2x, it becomes 4x. And finally, we have basic integration. We have 1/4 integral of 1 minus a half is a half, and then minus 1/2 of cosine 4x dx. So these are now basic integrals. The integral of 1/2 is going to be 1/2 x, and the integral of cosine is positive sign, so minus 1/2 sine 4x over 4 plus c. And when you are integrating sines and cosines that have numbers here, those numbers end up in denominator, if you remember those formulas from chapter 4 with the a, right? Sine and cosine of ax, you get divided by a. Now we're just, we can factor out another half, so this becomes 1/8 of x minus 1/4 of sine 4x and everything plus c. Yes?
Mine did a little bit differently.
What do you mean differently?
When you got to the when you got to the 1/2 minus 1/2.
1/2 minus 1/2 cosine to the cosine 4x?
Wait, the one over that. To the right,
Here?
The one over what you just said about.
Yeah.
1 minus the 1 plus cosine 4x over 2. Sorry. I made it so it's 2 minus.
You can't make it 2, it's half. Because when you combine, oops.
Never mind.
When you combine these, you get a half. And then you have this one, which is a half cosine, which is the second one. And then you Then you integrate each one.
If I said that that equation with the 1/2 minus 1/2 cosine 4x equals sine 2x. Is it okay if I say that?
This? This
Yes.
equals sine 2. Why would that equal sine 2x?
Because when you put it under a single 2, you get 1
It-
minus cosine 4x over 2, which is the
No, but it's a squared.
Sorry, that's
It's a sine squared. Yeah, yeah, yeah.
Sorry.
Has to be squared then. Yeah. It's all good.
That's right.
We came from there. Yes.
Where it says 1 minus cosine squared of 2x, could you turn that into sine squared 2x and then use the power reducing?
It will be the same thing, yes.
So then you would just do it and then it'd be 1 minus
Yes, this over here can be written as sine squared 2x,
and then you can use power reducing.
and then you will still use power reducing, which will still bring you there.
Okay, cool.
Yep. There are many ways to solve these problems. So good. See? We're already going great. All right. So far, we use the fact that integral of sine x dx, well, let me do a. Integral of sine ax dx is negative cosine ax over a plus c, and another formula, integral of cosine ax dx is equal to sine ax over a plus c. So these formulas are from 4.9, guys, all the way from Calc 1, and they include this constant a because, as you can see, they just pop up. As soon as you start using power reducing, it will become 2 and 4 and 8, right? Depending on how many power reducing formulas you have to use. Do you know how? Well, okay, so here is something that, since you're all gonna go home and this weekend is coming and you have a lot of time to kill, right? You change this to a 4 and see what type of a horror that's gonna bring. Because now you're just going to have a nested power reducing times another square. So, you should be able to grind through it in about 40 minutes. It should be okay. It's an excellent exam question. So that's sines and cosines. I just want to sum up that when you have integral of sine to the n to the m x cosine to the n x dx, you have two possibilities. One or both are odd. The method is peel off one odd sine or cosine, and from there on, right, use Pythagorean identities to transfer the rest. It's a procedure that we used for the first example. We had odd. You can have even an odd as long as one odd. That's the one where you peel, because you peeled off one, the rest will be even, and you can use the Pythagorean identity to transfer all the other ones to the other trig identity. The evil one is when you have two evens. That's the bad one, right? So you can have this situation, or you can have both even, right? So that's the evil one, because we use power reducing. and it will always be a mess. What I have done is the cheapest possible problem that you can have. Sine squared, cosine squared. If I bump either of the two powers to a 4, it doubles the work immediately, which is what I said. You should try that one at home, right, with a 4. And then we can also do it in class next week. But it's good for you to see what's happening. And we are done with the sine-cosine pair. There is nothing else, guys. There is nothing else that you can do with the sine-cosine pair. You either have at least one odd, which is the first method, or you have both of them even, which is the second method. And we are done with sine-cosine pair. We are moving to the secant-tangent pair. And this one is much trickier because you don't have the straight integral of sine is cosine and integral of cosine is sine, right? Now you have integral of secant tangent and integral of secant squared, right? So you have to be careful what is that you leave in the bank for your u sub, right, and so on. So let's see. We have the formulas integral of secant squared x. Should I go with a? Sure, let's go with a. Secant squared of ax dx is going to be tangent ax over a plus c. Patience, young Padawan. And the other one is integral of secant ax tangent x dx, which is going to give you secant ax over a plus c. So these are your formulas. Put those on the cloud, right? That's from Calc 1. They are enhanced by this a. And with this, you are going to also add the Pythagorean identity that 1 plus tangent squared is equal to secant squared. So when you add that one, there is no power reducing for these puppies here. So don't. We'll make it up in much worse way. Trust me. So we are going to start here with something that, you know, maybe we can call simple. Say you start with the integral of secant to the 9x tangent cube x dx. So this is what the cheap problems would look like. So why is this cheap? When you look at the formulas up there, you see that the secant tangent, right? And the integral of secant tangent is going to be secant whatever. Let's just make it a little bit cheaper for the first example. I'm just going to kill that 3. It's still easy because the tangent, it's easy for me. I'm sorry. The tangent squared, right, that will remain when you peel off one tangent. The tangent squared you can kick into secants using the Pythagorean identity. But let's do the vanilla example first. All right, so put a 9 there and tangent x and let's go from there. So if I pick u to be secant x, then the du is the derivative of secant, and derivative of secant is secant x tangent x dx. So you see that you can steal one secant and, you know, push it with the tangent and the dx for the du. So that's the game you have to play, right? So you are going to now put 8 secants on a pile, and then have secant x, tangent x, dx in the bank for du. And since u is equal to secant, this problem turns into u to the 8 du. So the whole mess just compresses into this quickly. And now we can integrate this one, get u to the 9 over 9 plus c, which is 1 over 9 secant to the 9 x plus c, and we are done. Now, let's say you care and you want to check this, hypothetically, right? So what do? Well, you differentiate the answer, right? The 1 over 9 secant to the 9 x plus c. You differentiate this. So the derivative is, you copy 1 over 9. The derivative of secant to the 9 is 9 secant to the 8x times the derivative of the inside of the 9, which is a secant, which is secant x tangent x. 9 will kill 9, secant times secant is secant to the 9, and that's the problem. Fair? So now what I'm going to do is I'm going to bring that 3 back into the mix, right? So now that's going to make problem look worse, but actually it's the pretty much same problem. So if I have secant to the 9x tangent cubed x dx, you still go and say, oh, I have a secant and a tangent that I can peel off, which leaves me with a secant to the 8x tangent squared x, and here is my secant x tangent x dx, which is what I'm going to leave in a bank for du. So now, because I'm leaving this for du, I know that u has to be secant x, so du can be secant x tangent x dx. So we know that. The issue is now that I have extra tangent. And that tangent we are going to deal with using the Pythagorean identity, where this, the hell is this? There we go. This tangent, right, is going to be secant squared minus 1. So this is secant squared x minus 1. And now you get to distribute and have, again, you can split in 2 integrals if you want to. So now you have secant to the 10x minus secant to the 8x, and then secant x tangent x dx. This immediately turns into u to the 10 minus u to the 8 du, because secant x is defined as u, and secant x tangent x dx, the whole string, becomes du. And now you have basic integrals. That's u to 11 over 11 minus u to 9 over 9 plus c, and then we bring in secant x. So 1 over 11 secant to 11x minus 1 over 9 secant to 11, secant to the 9 x plus c, and problem solved. Great. Time to cry. Because the previous method doesn't work now. If you peel off a single secant and a single tangent, you are left with odd exponents. And they don't transfer through Pythagorean identity. Technically, anytime you see even exponents, it's immediately, close to apocalypse. So it doesn't work anymore, right? But then, if you look at the other formula, the one where you can, what is the derivative of tangent? Secant squared. Woohoo! That's exactly what we have. Secant squared. So, if we just now flip and say u equal tangent x, and du is immediately secant squared x dx, this problem just becomes immediately u to the 6 du. So going from holy nightmare method doesn't work into solution right away. Right? So u to the 7 over 7 plus c. Guys, it's going to take time. This is where your weekend is going to go, right? It's going to take time to get comfortable with, u is secant, u is tangent. And then there are those problems where those don't work either, like the next one. So 1 over 7, tangent to the 7, x plus c. This is where the software which solves these problems can help you see, you try it 2-3 times, doesn't work, then, take a look. Don't spend 5 hours on a single problem trying to figure it out on your own, because when you are learning, you are supposed to follow examples and analyze examples first, and then, you take a look at the homework. Obviously, if you go home and just try doing the homework for this, it's just going to be terrible. He has to, right? Because this stuff is not easy. Yeah, it's a lot of different patterns, and it takes time to get used to these things, right? What happens if you see the problem like this? Square root of tangent x secant to the 4x dx, right? That's a possibility. And right, you say, tangent x is under the root, so that's definitely going to be my u. Great. The derivative of tangent is secant squared, right? But you have secant to the 4th. So what do? Split and then transfer the secants into tangents. Right? So it's a process to learn to see, where to break it up and how to transfer. So this is going to be square root of this. We have the secant squared x, another secant squared x dx, and I'm going to put the second one over here into the bank for my du. So if u is tangent x, then my du is secant squared x dx. But I still can't do this because this is a square root of u. I still have this one, so I have to transfer that one into tangents first. So secant squared is 1 plus tangent squared x, and then I have to multiply that by the square root. So it's integral of tangent to the 1/2 x, because then when you multiply 1 with the tangent to a half, plus now tangent squared, so that's 4 halves and 1 is 5 halves, so tangent to the 5/2 x. And then you have your secant squared x dx, and finally you have your u's. U to a half plus u to 5/2 du, and now when you integrate, u to the 3/2 divided by 3/2 plus u to the 7/2 divided by 7/2 plus c, bring in the tangents. That's going to be 2/3 tangent to 3/2 x plus 2/7 tangent to 7/2 x plus c. The skill to master here, not just knowing the formulas, but also the skill is to know to break it apart. You're either peeling one off or you are peeling two off, depending on what you need for your dx to leave in a bank for later. Now, there is no infinite amount of ways in which you can do this. You try one way, if it fails, you try the other way. Generally, you should be restarting the problem no more than 3 times, right? First, second, third, yeah. So 3 times, you should be getting every problem on the 3rd shot at most. Meaning you made the wrong choice, again you made the wrong choice, the 3rd one has to work out. Because it's not gonna be a problem that you can start in 6 different ways, right? It's one of the 3. And there are certain problems that you have to really learn the way to do them, because there is no the method like we just did where you, I leave this in a bank for du or du. It's not actually u sub at all. And the best representative of these worst problems is secant cubed x dx. That's the one that I labeled as the evil one. So to solve secant cubed, you have to, well, generally what people would immediately do is break off break off secant squared and the secant, because there is literally nothing else you can do, right? This is the only thing that you can do to start the problem off. As soon as you have a secant squared, options open, because you can use the tangent thingy, right? You can use for a Pythagorean identity. When you have secant squared, there is also the possibility of a du with a tangent substitution and all of that kind of stuff. So the things open up to you when you break it apart. As a secant cube, there is absolutely nothing you can do, right? It's just dead in the water. But here, when I have secant and a secant squared, now I have options, right? And the 2 options are, one is to transfer this secant into tangent squared and see if I can do anything from there. The other option is to, which obviously doesn't work, is to use u sub tangent. U is tangent because du would be secant squared, but I don't have a tangent, so that is immediately right. So neither of the 2 options that we are used to works. And this is what makes this problem evil. Well, since everything that we know failed, identities failed, which is Pythagorean identity, u substitution failed, right? What's the next thing we can do? Integration by parts. Exactly. So integration by parts over here, u equals secant x and du equals secant squared x dx, because you can integrate secant squared. Sorry, dv, I meant. So integration by parts is dv. dv. So your du is, what is the derivative of secant? Very good. And the integral of the secant squared is tangent x, right? Now you put that always helpful arrow, and you have secant x tangent x minus the integral of tangent squared x secant x dx. Yes, the Hydra. The Hydra, wow. Secant x, tangent x, minus, and now we are converting this tangent squared into, actually I have to move this a little bit down because I need some space. We need to convert this one into secant squared x minus 1. And when you multiply now, you are going to have secant cubed x minus secant x dx. And you can split the integrals. There we go. And as you said, Hydra, right? You remember the evil one? You have the secant cubed x on the left side, secant, oops, I forgot to cube. Secant cubed x on the right side. They add together on the left-hand side as the secant cubed x dx, leaving on the right secant x tangent x plus the integral of secant x dx. So this becomes now integral of secant cube x dx, which is the problem we're looking to find, is the 1/2 secant x tangent x plus the integral of secant x dx plus c. And now you go, hold on, what's the integral of secant? Right? What's the integral of secant? Well, that's a whole new nightmare by its own, which we are going to do now. I know, right? We could have done integral of secant first and then integral of secant cubed, but you know what? Those two are the pair to behold. Well, the same thing goes with a cosecant cubed and a cosecant. These pairs are identical, it's just minus signs all over the place. So technically this is the solution, but now we want to know integral of secant x dx. Now, as a student, I pretty much checked out on a secant cubed, and then, you know, for the single secant, you know, you might come up with the integration by parts, right? For secant cubed, I guarantee you're not going to come up with this for the secant stuff, right? Because you have to multiply by the particular function. And when you do that multiplication, then the problem transforms into something that you can do. So here is the way to do this. Again, I checked out and I just memorized the answer for the integral rather than to compute this every time, because I didn't want to memorize. It made no sense to memorize the function that you have to multiply into this so that you can do the integral. So here it is. Integral of secant x needs to be multiplied by secant x plus tangent x divided by secant x plus tangent x, and then you have dx. So this is where you start. And Then you have integral of secant squared x plus secant tangent. So secant x tangent x divided by, and I'm just going to go with the tangent x plus secant x. I'm just going to swap their order for the denominator, dx. Now, dare I say, it's obvious now that we use u substitution, right? Because if you set u equals tangent x plus secant x, you see that the du, the derivative of tangent, is the secant squared x, plus the derivative of secant is secant x tangent x, which is exactly what you have. So why is this function chosen? Because it works. Yeah. Welcome to Calc2. The function was chosen, the orange function is chosen because it works. Now, I just want you to bake on this little, someone figured that out 200 years ago, okay? It's either Bernoulli or someone along those lines, right? Was staring at this and said, oh, obviously, secant plus tangent divided by secant plus tangent, and just worked out this thing in 2 steps, and it's like, yeah, it's obvious. Right? Someone did that 200 years ago. So now the whole problem collapsed to du over u. And what is the integral of du over u? Beautiful. ln of absolute u plus c, which gives you what the answer for the integral of a single secant is, which is secant x plus tangent x plus c in absolute terms, right? So now when you are tutoring someone in Calc 1 and they come up with the, oh, so what's the integral? Because they did, oh, integral of sine, integral of cosine, then integral of tangent. Yeah, you can do u sub sine over cosine. And they can say, so what's the integral of secant? And you go, let me show you the function you will never think of, okay?
You just multiply by 1.
Yeah, that's exactly what it is. This is just 1. It's one of the, many ways you can write 1.
Do you think he just tried it and he's like, maybe multiply by...
I highly doubt that. I just think the person looked at it and said, it's obvious. Because some brains just work that way, okay? You have to accept that at this point. Right? So now we can write this, guys, as a formula. Aren't you excited? Yeah, integral. I mean, you don't, obviously you can do it, right? Integral of secant x dx is ln of secant x plus tangent x plus c. And, boom, there we go. Calc2 helped us figure out the basic trig integral, right? With a quotation mark on basic. So this is what the 7.3 looks like. And you really have to study sine cosine pair and then secant tangent pair. What is happening with the cosecant cotangent pair? Well, it's the same as secant tangent, just has minus signs everywhere, right? So if I am to work out, let's say, this problem here, if I'm to work out this problem and instead of square root of cotangent, cosecant, blah, 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 I'll just have a minus sign at the end, right? Because the integral and the derivative between the pairs is the same, just you're using different function, obviously, and they have minus signs. So the cosecant cotangent pair just gets to be annoying in terms of, oh, did I have all of my minus signs in a spot? So let's take a look at least one problem of those so that we say that we did everything, right? So this is going to be cosecant cotangent pair, and I'm going to still write the formula that the integral of cosecant squared x dx is negative cotangent x plus c, and the integral of cosecant x cotangent x dx is negative cosecant x plus c. So these are the two formulas, and as you can see, they follow exactly the same rules as the secant tangent pair, just have minus signs floating around, and you have to be careful to include those whenever you need to. So now let's say we come up with a function, the integral of cosecant to the third. That's going to be your homework assignment, because it's going to be the same. What should we do? Oh, you have the book. Oh, beautiful. How about we pick one of the homework exercises, because they are wonderful. Am I going to regret the cotangent cube? Let's see. I don't know. Cotangent cube, theta d theta. They have thetas there. And they also want us to compute this one from pi over 6 to pi over 3. Okay. So I have myself a cotangent over here. And we know that we can't do anything with the cotangent cube. There's only one thing that you can do at this point in the game. And that is split it. Yes. So there is nothing else that is going to work other than splitting into single cotangent theta and then the cotangent squared theta d theta. And this is where the options open, right? So now we get to see what we could possibly do. So for me to work on a cotangent squared, right, I need to have cosecant, because the derivative of cosecant, no. See, I'm already lost. The derivative of cotangent is negative cosecant squared. The derivative of cosecant is negative cosecant cotangent. So what do we do? Well, if you don't know what to do, you immediately start writing. That's the way to do it in mathematics. If you're stuck, start writing, because you have options, and you just start exploring those options. No one said that you're not playing chess over here. You don't have to see 5 steps ahead to, and know the solution to solve the problem. You just need to see 1 step ahead. That's all, right? It's not chess. It's much easier. So what do? You have option to transfer this into cosecants and then see if that's going to help. So what we know is that the cotangent plus 1 is a cosecant squared, right? So it's going to be cosecant squared theta minus 1 when you transfer this. And then you just write this integral, and if you don't like it, you can erase it. So you have the cotangent theta cosecant squared theta minus cotangent theta everything d theta. And you now only worry about the first integral. The second integral is easy. Why is the second integral easy? Easy. Why? Guys, integral cotangent.
Yeah. Oh, you just make it
Cosine over sine, use a basic U sub, you're done in a second. Exactly. So that one we don't have to worry about. The first one, can we solve the first one, right? What do we do there? So you have your cosecant squared. What is the integral of cotangent? Cosecant. Yep, so now it's just U over here. Good. So let's just rewrite this and set it up for our U subs, and then we have to deal with limits as well. We still have the pi over 6 and pi over 3, so we haven't done any substitutions yet. I'm going to leave the cotangent theta, cosecant squared theta, and now I'm going to put d theta. So that's the first. The second integral is separate integral. It will have a separate substitution, so I have to break it off, and I'm going to write it as the cosine x divided by sine x, because we are sorry, not x, theta, because we are going to use the separate substitution for that piece. So for the first piece in blue, u equals cotangent theta, because the du is going to be negative cosecant squared theta d theta. So I need this negative. I don't need this parenthesis, so I'm going to kill the parenthesis. And I just need this negative sign for the negative cosecant. Now in orange, on the other side over here, u equals sine x. No, lies. Can't use u because u is cotangent. We use g. So g is sine of theta. And then dg is cosine theta d theta. Now I also need to transfer the limits, so we can deal with limits. We have a negative integral of u du. So that's very cheap. On the other side over here, I have the integral of dg over g. So they're both easy. I just need to figure out limits and we're done. So for the orange limits over here, because that's easier, let's deal pi over 6 into sine. Sine of 30 degrees is very good. And then sine of 60 degrees is excellent. So you have your root 3 over 2 and 1/2. That was very good. Now we go with a harder one, with the cotangent, right? So what is the cotangent of pi over 6? Is going to be square root of 3. Good. And pi over 3? Very good. All right. So we have the values. And then we just compute. The integral of negative u is negative 1/2 u squared, and we have our root 3 and a root 3 over 3. We are not going back to thetas, because that would bring back the trig functions, that will bring back the pi limits. We convert those limits when it's easy, so we don't have to worry about trig limits later. Minus the ln of g, and g is given as 1/2 and root 3 over 2. So now we compute this. We get negative 1/2. When I square the upper, I get 3 over 9. When I square the denominator minus, I get 3. And that's great, because that's going to be negative, and it's going to kill the negative in front. Minus ln of g over here is root 3 over 2, and then plus ln 1/2. We can drop these absolute values because these are positive numbers. Minus in front of ln, and the minus from fundamental theorem of calculus gives us a plus there. So now I have, that's a 1/3. So that's negative 8/3. So negative 1/2 times negative 8/3. And over here, I'm going to write this as plus ln over 1/2 minus ln of root 3 over 2. So now when I multiply, these guys cancel. I get 4/3. Right? When you cancel 8 and 2, you get a 4 over 3. Positive. And then plus, you get the ln of 1/2 divided by root 3 over 2. Because the subtraction, which should be the answer. Well, then it just means it's just done. You cancel halves and then it's just 1 over root 3 and rationalize, you're done. It's going to be in notes. Ta-da! Look at that. We ended the class 50 seconds early. See, it's called efficiency. See you next week.